Hi, folks. I'm Vanessa Sochat. I'm a principal computer scientist from Lawrence Livermore National Laboratory, and I'm here today with my colleague Daniel Milroy. We are going to give you a talk called Lessons from a Market for Compute, a Bid for the Grid. Let's get started. So this is a question that we as system software developers ask a lot. What might the future look like? And from this perspective, we're often thinking about infrastructure and scheduling. I'm going to guess too that you often ask this question. And so we have a very opinionated answer to this question. We think the center of the future for high performance computing at a national lab is going to be autonomous and agentic. Now, here's the slide where I'm going to tell you, you and I, we really aren't so different. But I really think this is the case, and let me tell you why. So, at the National Lab, we run a lot of scientific simulations that need to be scheduled, multi-tenancy, multi-users. I have heard, I think, that at banks or other financial institutions, you are running many simulations overnight. Not only are you running them overnight, you're trying to solve a lot of the same problems. So high throughput, low latency, distributed. And you need those simulations to be done by the morning. So we both have this problem of scheduling and submitting jobs. So let's now talk about these schedulers. Here's a scheduler that you may be familiar with. You probably are. IBM Spectrum Symphony. Now, this is not an open source scheduler. I have never used it, but I took a look at it and I get the sense that it's optimizing for low latency, high throughput jobs, distributed, and with very strong service level agreements or SLAs, because you absolutely need to get those risk calculations done by the morning. Now, if you look at the topology of the resource manager itself, you don't have a lot of control there. There's a resource manager. You were probably creating a session and then you're submitting your task to it. And so the purple on the bottom, that is the user task. That is what you do have control over. Now let's take a comparison to our workload manager at Lawrence Livermore National Laboratory. It's called Flux Framework. Dan is going to be talking a lot more about it, so I won't go into details yet. But what it's going to give you is this level of portability. So it gives you portability layers and custom scheduling policies. So what do I mean? Well, you can launch Flux as a system scheduler on an HPC system across servers of a compute. That's probably not very different whether you're running in a financial institution or not. And then you can actually launch a child instance of Flux under Flux. And you can keep recursively doing that. But what's so powerful is that you control these child instances. Each one has control with respect to the scheduler policy. So how you decide to submit jobs, you probably want to submit them differently in a middle layer, for example, than you do on a bottom layer. And it's also going to give you control in the topology, how you're interacting with the resources. So along with being a portability layer itself, this scheduler is also going to give you the ability to do high throughput. So let me try to best explain the problem as I understand it. So in this talk, we're going to give you a brief demo of running a Monte Carlo simulation using Flux. It's not going to be perfect, but I promise I did my best. And so the basic idea is that overnight, you're running a bunch of different flavors of Monte Carlo simulations to assess the risk of your investment portfolio. They have to be done by the next morning because you need to turn the numbers in. And so these are different variants of Monte Carlo, the VAR, the value at risk, and the XVA, the X value adjustment. And basically, you need to do huge fan outs of all these tiny little jobs, and each of them is going to be spawning a million different scenarios, calculations, coming up with a value that says, okay, I have 99% certainty that this is not going to turn bad by tomorrow morning. And so in terms of your goals for how you're running this, it's about utilization. It's about grid packing. It's about getting the most bang for your buck in terms of how you design the scheduler. And so the scheduling is really a problem of cost, throughput, low latency. And interestingly, because you need to be able to reproduce the result, if you give someone a result, you need to be able to run it again and show them reproducibility is really important for you. Now, this was surprising for me because we in science, we had a reproducibility crisis in the early 2010s. It was based around science, and basically there was a very famous paper that was published that said, you scientists are not doing a very good job of giving enough in your papers to reproduce the work. And we were like, oh yeah, kind of. And that led to a lot of interesting developments in the technology space, but we both share this problem in terms of reproducibility. I thought that was kind of interesting. Okay, so let's now look at this demo. We are going to be actually running this layer. I put this together. I hope it's okay. We're going to start with a workload where we have 25 positions across 5 different scenarios for a total of 125 tasks, and we're going to seed them so that we can reproduce them and run them again. We are going to schedule them and submit them to Flux. That is just going to be a Flux submit. I'll show you what that looks like. Then for each task, that's going to be basically a Python script called priceoption.py. This is going to basically be running the Monte Carlo simulation. So in each task, this is going to be a million random market moves. Each is going to turn into a simulated end of period with the geometric Brownian motion formula that is shown. By the way, Brownian motion is also a science thing. That is how molecules disperse through cells. And actually, there's a bunch of things in the real world that use Brownian motion. I'm sure you know that. We are going to take the option payoff and then discount and arrange to get the price. Check it against Black-Scholes to make sure we did okay. That is going to write a JSON file with the result to the file system. I'm sure there are better ways to do that or different ways. For our simulation, that's going to be fine. Then we're going to reconcile. So we're basically going to check that we have all the results that we think. If we don't, we're going to use that same seed and we're going to submit them again. And then finally, we're going to aggregate into a report. And that is going to be the P&L, the profit, and the loss. So here is the actual, what that might look like between IBM Symphony and then Flux. So on the left in IBM Symphony, you may, define your class for a pricing service. Here we can see that we're creating a session because we're connecting to it running somewhere else. Then we're basically going to do a for loop and we're going to send the tasks. We're going to get the results. Now in Flux, you actually can do this in a language. We have language SDKs for Python, Go, Rust, of course, the different flavors of C, and probably a couple others that I'm forgetting. But then, so you could do it in this SDK, but most people will just run a Flux submit from the command line. So that's what that might look like. I will note we also have a Flux bulk submit that probably would be better for this task, but to do it in a loop also would be okay for the demo. And we can also do the same from within Python, and then we aggregate the results. So what is Flux going to give us? Well, I would like to discuss this after. I'm just kind of interested in the different kinds of topology that your tasks might need once you get below the layer of distributing out to different centers or different resources. When do you need CPU? When do you need GPU? When you need to actually specify the topology of a particular run that you do. For example, you might want to say that, okay, this particular job is going to need GPU and connecting to the network, so I want to schedule this in a way so that those devices are close together. Let's talk about this afterwards. Okay, so I'm now going to hand it off to Dan, who's going to kind of dive in and tell you more about the Flux framework.
All right, now I want to provide a bit of an introduction to the Flux framework, and hopefully you can understand how national laboratories run scaled compute or on-premises HPC or in cloud plus HPC converged environments. So first I want to get into a little bit about what the Flux framework is. It's also known as Flux, and it's a system or user-level workload manager developed by the Lawrence Livermore National Laboratory that combines hierarchical job management with graph-based scheduling. So these two key features, job management and scheduling, if that division between them is a little bit foreign to you, hopefully by the end of this presentation it'll be less so. One of the key facts that I want to highlight is that Flux recently joined the High Performance Software Foundation, or HPSF, which is part of the Linux Foundation. Now, Flux also has well over 25 contributors at this point, including some of the principal engineers who created Slurm, which also originated at the Lawrence Livermore National Laboratory. Now I want to get into a timeline of how Flux came to be. So the project was actually established all the way back in 2012 and then started design in 2013. The first Flux instance was created in 2014, and this was a prototype that allowed Flux to be instantiated underneath external resource managers and schedulers such as Slurm, and this is the way that it was deployed initially. Flux Core was actually released on GitHub in 2016. And by 2018, the first publicly available science was done in the context of the Pilot 2 Cancer Moonshot Ensemble. Now, by 2020, the first system instances were released. So this was instances or releases of Flux cores that actually had the ability to completely manage and schedule an entire cluster. By 2021, the MUMI workflow was created end-to-end. So this was deeper integration between Flux and MUMI, which was used for RAS or RAF membrane dynamics. So this was, again, kind of an extension of the Pilot 2 Cancer Moonshot. By 2024, El Capitan, which debuted at #1 in the top 500, was launched with Flux actually scheduling and managing the entire cluster as it still does today. Then, as I mentioned before, in 2026, Flux joined the High Performance Software Foundation. I should also mention that in 2021, along with the MUMI workflow, the team won the R&D 100 award. So one of the key capabilities that Flux enables is actually the ability to support emerging workflows. So think complex scientific workflows that integrate many different components together. So these are heterogeneous workflows composed of heterogeneous components. So what I mean by that is consider, for example, the MUMI architecture. So this is a re-architected, newer version of MUMI. And again, this is something that models cancer-causing interactions or protein interactions. So you have a structure generator, and that is represented by machine learning or uses AI. Then it couples together more traditional HPC-based simulations. So think, for example, CG analysis. Then we have the orchestration component. So this is the workflow manager that interfaces directly with Flux. Then you have services. So think, for example, communications libraries like RabbitMQ. And a question for the audience that I want to pose is, think for us, or please help us understand what kind of complex heterogeneous workflows is your community using, or are you having trouble orchestrating at this point? We'd love to understand what your difficulties are and hopefully work with you to solve them. Flux was actually created to address post-exascale challenges like MUMI, for example. The architecture is designed to solve resource management challenges, which also serve to bridge the gap between traditional batch capabilities and the needs for modern dynamic workflows. So Flux runs on big computers. I want to highlight that, again, it is the exclusive system-level scheduler on the NNSA exascale system, which is El Capitan, which is currently #2, and also 5 other top 500 supercomputers. Now I want to get into some details about what the Flux hierarchy is and how this enables important capabilities for complex workflows. So I mentioned before that there was a division between scheduling and resource management. Well, this modularity is hugely beneficial. This enables kind of decomposing Flux into components, and it also enables hierarchical management. So hierarchical management, for an example, allows Flux to be instantiated inside of itself or inside of an external resource manager or orchestrator. So think Slurm, LSF, Kubernetes, etc. So Flux, after it is instantiated inside of one of these resource managers or schedulers, it can actually create its own overlay network, its own instance, its own niche scheduler, and then further subdivide the resources by deepening the hierarchy, by increasing the number of instances, each with its own overlay network and own queuing system and own scheduler. So this enables scheduling decisions to be distributed across multiple levels of the hierarchy, and as I said, to kind of fine-tune what those scheduling decisions are. This enables fine-grained management of resources and the ability to optimize how resources are managed at each level. This also can improve throughput, so jobs can actually be processed as low in the hierarchy as possible. So you can think, for example, you could block off a large number of resources, create an instance to carve out resources from an overall pool, then create further sub-instances that have maybe simpler schedulers that increase the throughput. So you can use a divide and conquer approach in this case. So Flux also enables converged computing. So think, for example, the ability to bring together HPC and cloud to have the best of both worlds. So in this context, typically when we talk about converged computing and the best of both worlds, we're thinking about combining the de facto standard cloud orchestrator, which is Kubernetes, with Flux in various formats. So think, for example, when you consider Kubernetes, the capabilities that it has natively, such as modularity, portability, enabling of automation, and also declarative management, versus Flux, which represents some key HPC capabilities like high application performance, support for low latency communications, fine-grained and sophisticated scheduling, and large application scale. And think that converged computing is basically the overlap, which is of increasing size between these two different spaces. Now, I also want to highlight a really important development, which was integration of Flux into Kubeflow to enable AI and ML simulations, coupled together with more traditional MPI-based simulations, which of course enable low latency communications. So the Kubeflow trainer is actually the industry standard for AI and ML training, and it's used together with, in order to support traditional scientific simulations, which are often informed by, so are use inference on top of or coupled together with AI ML model training. So many or frequently scientific simulations require CPUs only, but also CPUs and GPUs together versus AI and ML models, which are predominantly use GPUs. So an example of this might be physics-based simulation or scientific workloads that are coupled kind of tightly together with AI ML inference and then training. Now, current Kubeflow MPI support, or previous rather, Kubeflow MPI support was limited in terms of the support for MPI variants and also constrained by complex and brittle SSH bootstrap. So bringing Flux into Kubeflow actually enabled much more rapid and reliable bootstrapping and support for many different flavors of MPI. Now, the Flux operator actually affords elasticity and dynamism. So this was designed to manage complex dynamic workloads. So think, for example, if you have multiple different components of a workload, you have an ML training stage, multiple ML training stages, ML inference stages that might be performed, as I mentioned in the previous slide, for simulation A or simulation B, which might use different types of CPUs or combinations of GPUs. The basic idea is that the resource needs of these kind of complex composite workloads can change over time, and the Flux operator was designed with integrations with Kubernetes in order to facilitate this sort of resource dynamism. Flux was also designed to promote and support systems research and innovation to kind of prototype novel scheduling algorithms, match policies, etc. And finally, I really want to highlight that emerging systems need flexible resource models. This goes back to what I mentioned before about Flux relying on and promoting a graph-based scheduling model. So you imagine resources can be modeled as network, power, storage, or future resources that haven't even been considered yet, can be integrated into our scheduler. And this model can actually express not just the resources, but their relationships together and how they can change in time. Finally, I want to tell you a little bit about quantum resources, which is an example of a custom resource or the example of the ability to integrate in new types of resources. So workloads for HPC and finance as well often need integration of many different types of resources, possibly dynamically. And this is represented here by two different sets of resources that could be underneath a cluster. You could have kind of traditional nodes, sockets, and cores, and on the other hand, quantum resources. And maybe you want to schedule them so that they're available at the same time. Classically, what can happen is you can have stalls because the HPC, classical resources, are waiting for the quantum or QPU to be available because of the second queue that is used to maintain the state of the quantum resource. So this is what we call the 2-queue problem. Again, this is where you schedule one workload manager's resources with work submitted that waits or depends on work that's submitted to another external queue. So you get actually idling of resources or kind of wasted resources and underutilization without such a solution. But with a solution that we've started implementing in Kubernetes, you can actually have successful co-scheduling that is synchronized in time. Thank you.
Alrighty, let's dive into actually running Monte Carlo on Flux. Remember that we have a 25 position book priced across 5 market scenarios for a total of 125 scheduled jobs. So we are going to be running this on my almighty powerful tiny little laptop, not really an actual workload manager, but that's okay. I realize I haven't told you how the agents are coming in. So we're going to be sharing some of our agentic work after this. But let me just briefly explain it to you now. So in this directory, we have this abstraction that's called a plan. Now, the plan is basically what we're going to be giving to an agent that's asking it to do a particular task or a series of tasks. So in this case, our tool is called Fractale, and this is a particular agent that we're asking it to run the simulation. We're saying, hey, agent, you're an overnight risk batch orchestrator running inside of a Flux instance. Your job is to evaluate a portfolio across market. You're going to be using Flux through provided tools. This is how you do different steps of your workflow. So you're going to plan, you're going to submit, you're going to monitor, you're going to reconcile, and you're going to report. These are the steps that I talked about a little bit earlier. Here's how to handle ad hoc requests. Here are rules for how you do this. So this is like the basic structure. When you're asking an agent to do something, you usually want to give it clear instructions of how it interacts. So this is the plan.yaml. Now, another piece of software that we use, which is very important, is called the MCP server, the Model Context Protocol, which is like the language that the agent that's running on my computer is going to use to talk to a server that's providing these particular tools. So actually, first, let me show you what it means to start a Flux instance. Do we have Flux in the container? We have Flux in the container. We found our Flux. Okay, so let's start a Flux instance. This Flux start, when you use a test site, is really just for kind of testing and demo, because obviously this is not a real machine with like size 8. It's actually much smaller than that. So with Flux, you do, okay, Flux resource list. What do I have? Oh, wow, look at that. I have 8 nodes and 64 cores. So actually, this is my one machine that's multiplied by 8. I don't really have that. And because we're running this inside of a VS Code dev container, we see that the node list is a lot larger than it actually is. Okay, so now we are going to start our MCP server. That, again, is another configuration file. This is fairly simple. So this is basically the tools that we're going to give our agent. So what you see here is we have tools that are for Flux. We have tools that are for general HPC that are interacting with the file system. So our agent's going to need to be able to read a script file. It's going to need to write and list directories. And obviously, when you're normally running this, you want to put it in a sandbox of sorts. So we're running in my dev container. I would not release any agent on my actual machine. We're going to start the server with MCP server start. You can see the startup here. I'll quickly kind of zoom up so you can see it. It's showing that it registered all these different functions. It's initializing an abstraction called a hub. I don't need to go into the details, but there's a hub and a worker mode. And then it's basically waiting for an agent to interact with it. So let's do that. So I have exported my Gemini API key into the environment. I am not going to tell you what that is. You can't have my Gemini. So basically, we're going to be using Fractale, which I think I've installed. Fractale. I have installed it. And we're going to be running that plan. And this is fully live demo. So I don't know. Sorry, it's live as I'm running it. It's not live as you're watching it. So you're right. I could just record it again. But it's live for me right now. And we're going to run it and we're going to see what happens. Let's do Fractale run plan.yaml. We're going to see what our agent does. Okay. I didn't set the environment variable. I'll be right back. Alrighty. So our token is exported into the environment and we are ready to Fractale run the plan. Let's see how our agent does. Okay, so we're loading up the prompt. Here's the prompt that's given to the agent. That agent is going to basically be pinging the Gemini API and then figuring out what tools to call. So what it's immediately doing is exploring its environment. It's listing files in the file system. It's reading the file to generate the workload because it doesn't see the task.json. It submitted job to write the task.json. It's doing this really quickly. I can't keep up. So it finds the file, it's reading the file system file, the task.json, because we told it to. We told it it needs to read the task from that file. It's submitting another job to test the script. There's the output that you see right there that it's getting in the result. Okay, so if that works, it's next going to start to actually run the different tasks across the different scenarios. So it looks like it's pausing a little bit. I'll probably edit this out. All right, so the pause there is because I'm using probably a model that's a little bit too powerful for the use case. I'm using one of the advanced models. And so the pause was probably literally the API thinking. And so we were waiting for a response. What you just saw was the stream of price options being submit that were read from that task.json file. And so now we are waiting again for the model to think. I'm going to edit out all these awkward silences. Awkward. I'll also give you a little insight to the structure of our particular library. what we do is we allow the model to give us many tool call requests at once. So when you see a stream of tool calls, it's because the agent prepared a bunch of them to be run at once. Then we equivalently have to give back the output for actually executing that work. We give it back the tool calls. So what it's doing now is it's going through this running of the job. We just called the aggregation of the results. We wrote the report.json. It's reading the report.json. We'll see if it likes the results. Hopefully it does. And we are done. Success is true. It's like, here's the output. The workflow is complete. So let's see what we have here. We have our task.json. So this is what was written by our script. So let's put it over here, and I'm going to make this smaller so you can see it. JSON. So here's all the jobs that were run. Probably a little bit much for the demo, but I have no regrets. I have no regrets. Okay. So the report. Let's open up our report. This is the final report. I don't know what any of this means, but there are 0 tasks missing. It found all 125. That's good. The very first time I ran this, I had a task missing and I was like, oh no, this didn't work. Okay, so let's look in the results. So in the results directory, we have each of these individual kinds of, I'm guessing, simulations that were run. Probably folks in this that are watching this talk know a lot better about this than me. So high level, what we just did is we wrote this plan and we said, hey, agent, these are the tasks that I want you to do, and here's how I want you to do it. We deployed an MCP server that had a set of tools for interacting with a workload manager and also interacting with a file system. We then started our agent running. The agent had access to the tools, had access to the goal, and basically just kept going. And here's an interesting point. I selected a more advanced model that was probably too advanced for the task. Now, this is something to think about. You may think that a better, more advanced model is always better, but for smaller tasks, you're actually going to get better performance in terms of speed when you use a smaller model. You don't always need the chunkiest reasoning model for what comes down to maybe a small task of submitting jobs. So let's go back to the slide. Alrighty, so drum roll. What did our very accurate real life scenario tell us about what the book is worth under stress? Let's look at what the numbers say. The book is net long convexity. It gains under both a crash and a volume spike. A 10% sell-off costs about $2,800. The same move up adds about $5,100. Each bar sums 25 Monte Carlo reevaluations validated against Black-Scholes. I want to get a sense of how agents might be able to help the financial industry. And I think a good strategy, a good way of doing that might be to share with you some of the work from our team, and then maybe something sounds a little similar and you can think of an analogous use case. So this is how we've been using agents in the last 6 months, I'd say, to do these kinds of tasks. So the first task is this general idea that when you're submitting work, so when you're running that overnight simulation, usually as a human, you have to write a lot of code. You have to write a lot of the submission scripts to do. And so in this future, in this agentic world, you're not writing those job specifications anymore. You're saying, hey, agent, I want you to run this HPC application on this many nodes, and I want you to optimize it in this way. By the way, I need it done in 6 hours because I have places to go. So when we did this, we had 1,000 open source job specifications and we translated to the Flux Workload Manager. These are the general issues that we hit. And it could be the case that when you're doing an analogous task for your industry, you run into similar things. So in many cases, when we had to specify a format of output, or especially something with templating, especially if the templating was specific to a workload manager, the agent might either leave it out or get it wrong. And so that's an issue with translation. Now, specific to HPC, one of the big problems was memory allocation. High level, this is a problem of when you're going from workload manager A to workload manager B, if workload manager B does not have a flag or a feature that workload manager A does, the agent isn't going to know what to do because you're going to run something and it may run entirely differently. And so the others are kind of similar. So topology and binding, That really is a slightly different case. Imagine that you have A and B. A has many different ways to specify something, bind to the resources in exactly this way, and B has a much smaller limited set. It's not always clear how to do that mapping. And then these last ones are definitely specific to HPC about MPI, job arrays. The environment is important, but I'll mention that because you're always going to have the task of environment variables, secrets, credentials. I don't know how that works in for banks or finance, but I'm guessing you don't want that leaked to an agent. And then, of course, dependencies and scheduling. So you're going to have to think about what happens when there's a dependency and the agent is translating to another workload manager that maybe doesn't model that in the same way. So the next capability is discovery. This is the idea that a piece of work, a job, lands on a resource that has a secretary agent. It says, hello, secretary agent. I have this piece of work for you. I want you to look at the resources that you see. I want you to look at your compute, your network, your software, and I want you to basically first figure out if you can do it. And then if you can, I want you to figure out the best way to do it. And if you can't, I need you to report back to me so that we send it somewhere else. So this is sort of a dynamic discovery of what you have. So what we did is we developed this resource secretary software that has a lot of different providers that are specific for kinds of HPC stuff. So you see that there's parallel technologies, there's hardware, there's network, there's storage, container technologies, workload managers. I don't know how much this maps to the finance world, but I can imagine that there's something similar. And this is going to allow you to dynamically probe environments and figure out what's there. And HPC would be like, hey, do you have lamps that's compiled with Cocos for GPU? Yes or no? Now, the other thing that we made is a specific server to provision agentic tools. So this basic idea is that, okay, we need something, a place for the resource secretary to live, and it needs to speak this language called the Model Context Protocol, or MCP, which is the standard for agents to communicate. It also needs to receive real-time events. So in your space, imagine that instead of having sort of a batch, like send them out and do it model, you have more of an orchestrated communication model where you have messages going back and forth, and you actually trigger some next model to run when you get a result back. So that would be an example of when you might be interested in real-time events. This is the basic idea that we have a particular task, and we're giving it to that same secretary agent. We're like, hey, can you run this? And if you can, give me back a proposal for what you think is the best way to do it. So what we found is that our agents were highly accurate, 87.7%. Not that 99% that I'm guessing your industry needs, but this is just a start. This is a first shot at it, and we were very pleased with that result. The next capability is optimization. So we basically ask agents, hey, I want you to build this application, optimize it for this environment, and then run it in a scaling study. But you can imagine that you'd actually have the agent, before running anything, you'd actually have the agent build the simulation for you. The simulation itself may have a dependency structure. Maybe you use container technologies. Maybe you have a different cluster that you submit to. So this is what our scaling study looked like. Build it, deploy it, optimize it at a small size, optimize it at a large size, get the figure of merit, and we're running this on the cloud. We're running this on AWS. We wrote a white paper for this. We had an agentic team. I will say that even though this was at the end of 2025, literally the end of November, this already feels like old work because of how quickly these models and the tooling moves. Here's an example of how our application scaled. So you're probably not familiar with HPC, but there's this thing called strong scaling, and it's the idea that when you have a particular problem and you feed it more resources, you should see your figure of merit, so how much science is getting done, increase relative to that. So seeing basically what looks like a linear line that yes, as we give it more nodes, as we give it more resources, performance is going up. And for this particular application on the right, for example, that's in the million atom steps per second. That's the right pattern that you want to see for a scaling study. Okay, so dispatch. This is this idea that once you've assessed a piece of a cluster for a piece of work, you then actually want to ask the agent to submit the job. So in practice, what this means is that the agent needs to transform a textual request into a job specification, and then run the submit command, monitor it, look at job info, maybe look at the log to make sure that it's running, and then return like, yep, did it, boss, it's looking good. And so what we learned is that dispatch is really reliable. And so the way that we assess this is that we actually had the agent do it. So we ran an application called LAMPS. And in practice, we found that LAMPS completes in about 150 seconds. So then when our agent did the transformation, so from the textual prompt to an actual job spec and did the submit and monitored, you can see the distribution of the actual times of running LAMPS that we had. And there were actually only 9 failures where it returned a 0 wall time, or basically like, I couldn't get this to run. Okay, capability 5 is orchestration. Can we get an agent to orchestrate an entire scientific workflow? So in our community, we have a tool called SnakeMake that is for the biosciences community. And we asked the agent to design the entire workflow from scratch and to run it. And the short story of this is that it did immensely well. 18 out of 20 had exact reproduction, and the way that we assessed this was based on actually looking at the integrity of the data, that the variants that were discovered in the data file. And there were only, let's see, there was one post-filter divergence. So that means that after the agent got a result, it applied another extra filter that wasn't necessary. And then to be fair, 2 of the jobs actually did fail. So there were 21 jobs total. So what is the elephant in the room here? We see he's purple. Hello, Mr. Elephant. I see that you're reading code, math, and AI books, so you're a very well-read elephant. The elephant in the room is resource contention. Now, I don't know the extent to which this applies for the financial industry, but a lot of work assumes that you can get what you want when you want it. And I'm guessing that for your community, you pay for the services, you pay for the resources, the hardware, everything, so you have them exactly when you need them. And maybe there's contention within your company, and you have to kind of work together to make sure that Harry's not running at the same time as Sally. Harry and Sally, it's a good movie. For us, it makes the reason why scheduling is so important, because we can't always guarantee that the resources that we want as scientists are available when we need them. So this is the reason why scheduling is important, especially when you have heterogeneous resources and you need to coordinate, especially when you have problems like you're trying to coordinate quantum, which is a separate queue, with your classical resources. You need this level of intelligent scheduling. So moving forward, the compute center of the future is built upon convergence, modularity, and agency. We believe that it is powered by the workload manager. And even though you are doing different things, I suspect that the workload manager is really important for what you do too. So on that note, let's have some discussion. Here are some questions that I'll bring up, and we are there to discuss them. And thank you for having us today.